Okay. So, hello everyone. So, I hope I am audible now. Can someone please confirm?
Yes, ma'am.
Okay. So, this is
Yes, ma'am.
the second week when we are dealing with this course, Robotics, Basics and Selected Advanced Concepts. I am Soumya and I am your TA for this course. Okay. And I'm a PhD student at IIT Gandhinagar, and we'll be together learning the concepts for 12 weeks. So last week we had a couple of basic questions, right? We saw very basic questions related to robots, and more and more technical concepts will be coming in future today as well. So have did you get a chance to go through the lecture for this week? I think your assignments are due soon. I guess it is on 4th or something. So did you see the lecture? You guys did not see? Okay. Suradeep says that he has seen. And rest everyone, did you go through the lectures? Because we are going to do question and answers here, and that would definitely be complementary to the lectures, but lectures are important. If you've not gone through the lecture, then try to understand what I am teaching today. But apart from this, going through the lecture is very important, because these sessions are complementary and they cannot substitute the session, because all the theoretical concepts are being covered there. It happens in 3 hours, 4 hours, etc. We do not have that much time, and we'll focus more on problem solving, right? Because once you learn the concepts there, then solving the problem should be done here, so that you get to understand the concepts better and clarify all your doubts in this interaction session, right? So it is good that you watch the lecture. If you've not done this time, make sure you do it from the next time. Okay. Apart from this, okay, I had to just suggest one thing, that do you guys have access to the recordings? I will share the link of the sheet here, so that in case you do not have, you can always go and access the recordings. Okay. So this is the suggest all of you to copy this link and keep it with you, because this link will be helpful in getting an access of all the video recordings. The post recorded lecture is also the link is pasted over there, and for the other lectures also I'll be pasting it over there. All right. Anyway, if you miss the link by chance, then you can go to my YouTube channel, and for this playlist you'll be able to get all the videos. So there is a playlist created for this particular uh, subject. Okay. Apart from this, there are three others. Two of them are from control systems, and one of them is for advanced robotics. And I'll give you some suggestions also today, that what you have to watch if needed from there. Okay. And okay, let's start the session. My plan is not to go with the first question. I'll go at a later point of time, sometime today itself. But I would start from even more basic question. Okay. So when we are solving the questions, I request everyone to have pen and paper with you, and please solve the questions. Uh, just sitting idle would not give you practice, and you replying to the answers is more beneficial for you, right? That's why. So please let me know the answers before I write. That is also good. Okay. So I request everyone to solve. So in this question, what is there? For ZYX body fixed Euler rotations with theta 1 30 degree, theta 2 45 degrees, and theta 3 60 degrees, the R22 element of the resultant rotation matrix is what? Okay, so we are rotating first about z axis, then about y axis, and then about x axis. This is the subsequent rotations that we are having about these degrees. And then we want to know if all these three rotations happen in this sequence, z about z, then y about y, then about x, then what is the final rotation matrix element and what is the R22 element corresponding to this matrix, right? So from here we know theta 1 is 30 degree, theta 2 is 45 degrees, and theta 3 is 60 degree, right? So we are asked to find R22 of the resultant rotation matrix, and it is an integer based question. Okay, so how are we going to do this? What do you think we should do? So I want to write the complete rotation matrix, which will be multiplication of three matrices, right? One matrix which would be rotation about the z-axis, then the other would be rotation about the y-axis, and the third one would be rotation about the x-axis. So it would be rz by theta 1 into ry by theta 2 into rx by theta 3, right? Once you know this, can anyone tell me what is the standard rotation matrix about z-axis? I mean, it can always be derived, but once it is derived, and I would suggest you where you have to look at the derivation. So I derived it in one of my earlier courses, which was for advanced robotics, and I'll direct you to that in some point of time. But before that, can someone tell me what is the rotation matrix about the z-axis? It's very standard and usually we remember it. It's not easy. It's just combination of sine cosine.
Cos theta 1
Okay.
minus sin theta 1, 0.
Okay. And
Sin theta, cos
क्या
theta
हुआ
0.
कितना ले कितना को है ना हाँ करूँ मेरे को है ना फोन कर ले
just a second.
Cos theta and 0.
Yeah. Sine theta 1, then cos theta 1,
Cos theta 1, 0
0, and
and
0,
0,
0,
0,
1. Yeah, very good. So, this is the rotation about the x-axis. So you can be given any arbitrary axis and we'll have them in one of the questions. But as of now, it is if you have to rotate about standard z-axis, then this is your rotation matrix. Okay. If you are supposed to write this rotation about y-axis about with the angle theta 2, so what you're going to do? It's going to be cos theta 2, 0, sine theta 2, 0, 1, 0, and minus sine theta 2, 0, cos theta 2. Okay. You see that sine and cosines here appear in first two rows, whereas in the next expression it appears in the side rows and not in the middle row and middle column, right? For our x by theta 3, it is 1, 0, 0, 0, cos theta 3 minus sine theta 3, 0, sine theta 3, cos theta 3, right? So these are your rotation matrices and these are very standard and it is good if you remember them. Alright, it comes after derivation, that if you are rotating about which axis whatever, so it comes after particular derivation. You should be knowing all of these rotation matrices. Okay, so what we basically want, we know that r is equal to rz into ry into rx, right? So can anyone tell me what would be the R22 element? Means it would be some matrix with some numbers, right? Right? What is R22? It is this element. Can anyone tell me after matrix multiplication what would be this element? I request everyone to solve this and tell me. No, not just cos theta 1 square. Square you won't get. Be careful in the calculation.
Cos theta 1 into cos theta 3 plus sin
Just a,
theta 1 sin theta
just
2
a
sin
second,
theta.
just a second. R22 is equal to cos theta 1 into
Cos theta 3
cos theta 3.
plus sin theta 1 sin theta 2 sin theta 2.
Very
All
good.
three important.
Very good. So it is just matrix multiplication, and after multiplying you'll get this term. This is perfectly correct. Okay. So then you can substitute the value of theta 1, theta 2 and theta 3. If we substitute it, we'll get uh, theta 1 is 30 degree, right? Theta 3 is 60 degree. And then what? Just a second. Theta 1 is 30. Yeah, theta 0 is 60 plus sine 30 degree, sine 45 degree, sine 60 degree. You just have to substitute these terms and come up with an answer. What it is, you can tell me. Come on, guys, answer. This is just substitution.
Zero 0.739.
Okay. Does anyone else also get the same answer? Okay. Okay, so it is a bit different, but Lakshmi, you are also in range. And Shravan has the correct answer. Okay. Okay. So from here, it would be nearly equal to 739. Okay, so this is your answer for this question. Yes, it is just differing by decimal places and the approximation that you have made. Otherwise, it should be same. So anything that you write in between 0.69 and 0.79 is considered correct for this answer. Okay, because you might have decimal discrepancies. Okay, so after this we want to deal with this question. And which of the following representation of orientation suffer from gimbal lock? Does anyone have any idea what is gimbal lock? No? Okay. So, okay. First of all, I need an answer to this question. If in our just normal surrounding, if there is a cube, no, leave cube. It is not kept on the ground. There is an aeroplane. Okay, and the aeroplane is flying. All right. Then can you tell me what number of degrees of freedom does it have? How many degrees of freedom does it have? Okay, Shravan Kumar is perfectly right. Loss of one rotation, that is true, but I'll come to that. How many degrees of freedom does this aircraft have? Come on, what is degrees of freedom? Whatever you know that works. Please answer. 5, 6. Okay. Venkatraman, can you tell me why are you saying 5?
It cannot rotate along the direction of movement. It's not expected to like rotate
It is
the
not
forward.
expected to do, but anyway, for let's say you have a drone or anything, or in what all directions and what all orientations it can have. Basically, I mean, the answer should be 6, irrespective of what it is expected to do or not expected to do. Okay? Yeah, 6 degrees of freedom. So, degrees of freedom represents the number of independent uh, and unique axis of motion, such as rotation or translation, that any robot can perform. Okay, so a higher degree of freedom allows greater flexibility, greater reach, and dexterity for complex tasks, whereas lower degrees of freedom are typically used for simpler, faster, and more efficient applications, but in that case they'll have it reduced. Sanjay, do you want to say something? Okay. Okay, so degrees of freedom is like that. So, for example, if something is in the space, it can move in x direction, it can move in y direction, z direction. It can uh, roll, pitch, and yaw. Right? Yes, yes, yes. It has. Ah, is someone unmuted? Okay. So the thing is, it has 6 degrees of freedom. All right. So what happens? What happens in gimbal lock? Ideally, there should be 6 degrees of freedom for such objects, and in other cases there can be other degrees of freedom. But what happens if we lose some degree of freedom? Then we enter into gimbal lock condition, and I'll tell you what it is. So gimbal lock is the loss of okay. Gimbal lock is the loss of one rotational degree of freedom. Okay, when 2 degrees of or two rotation axes become aligned. I request all of you to take a note as well. Become aligned in an Euler angle representation. So the best example is that of aircraft, right? And what happens? So let's say your aircraft is flying. Okay. So it can have XYZ motion. Apart from that, it can roll, pitch, and yaw, right? So if it can, what is meant by rolling? So rolling is uh, about, let's say this is your axis. Then if you move it out about this, it is rolling. If you move about this axis, like up and down, pitching, if you understand, it is pitching. Like about all the three X, Y, and Z, the motions are roll, pitch, and yaw, right? So what happens in aircraft, let's say it is pitching at 90 degrees. What does that mean? Aircraft is in this state, somewhat. Okay. And it is at 90 degree, or it is at plus 90 degree. If it is in upward direction, then what would happen? Either you roll or pitch, both of them are non-recognizable. You would uh, lose 1 degree of freedom. So I think I can show this with the help of a video to you. That would be much more clear in 3D. Just a second. Okay, I'll have to change window capture to okay, and I'll have to present the screen to you. Okay, I hope my screen is visible. So let's check this.
Imagine conducting every part of your research only on one platform. Meet Boreum.
Ever wondered how we describe the orientation of an object?
So this is basically a cube, and then we are defining the orientation of this, and then you get a sense of Euler angles here. How do you rotate about each of these axes, and then the angles are defined. But what happens if one of the angles, how do you lose one rotation when both the rotation axes coincide? So that is what we are going to see in this video. Please watch carefully.
Ever wondered how we describe the orientation of an object in 3D space? How would we define the rotation of this cube from here to here? One common way is using Euler angles. Euler angles break down a complex rotation into 3 simple chained rotations about the axis of the cube to represent any 3D orientation. Let's look at this cube. This cube has 3 axes, the X, Y, and Z axis. This cube starts out oriented with the world reference frame X, Y, and Z. To model this rotation, we will follow a Z, Y, X rotation sequence. First, we rotate the cube about the Z-axis by some angle psi. When we do this, notice that the X and Y axes of the cube have been rotated by psi, creating a new local axes X' and Y'. We then move on to our second rotation. This time, we rotate the cube about this new Y' axis by an angle theta. This rotation rotates our Z and X' axes, creating a new Z' and X" axis. Finally, we rotate the cube about the new X" axis by an angle phi. This rotation rotates the Z' and Y' axes to become our new final X', Y', and Z' axes. We now have represented our final orientation by breaking one complex rotation into 3 simple rotations with 3 angles. You may have noticed that I chose a specific convention Z, Y, X, representing the order of axes that we rotate about. What if we chose to rotate by X, Y, Z? Well, let's try it. When we do so, we get a completely different orientation. When we define these rotations, order matters.
So ZYX is not same as XYZ, right? Both of the orientations are not same. The matrix multiplication, the order in which you multiply, has an effect.
helicopters. This ZYX convention is especially useful in aerospace because it's so intuitive to understand. Let's swap our cube for an aircraft. This aircraft has a frame with the x-axis out the front, the y-axis out the right wing, and the z-axis pointing down. Using our ZYX convention allows us to define the aircraft's attitude with three familiar terms. The first rotation about the z-axis gives us our heading, or yaw. The second rotation about the new y-axis gives us our pitch angle.
This is called pitch, okay? Be careful with what is happening. Pitching is in the forward direction, the aircraft leaning downwards and upwards.
And finally, our third rotation about the newest x-axis yields our roll angle. This direct mapping to yaw, pitch, and roll makes Euler angles perfect for pilot interfaces and high-level descriptions of flight. However, this convenience comes with a severe drawback that we call gimbal lock. Here, our cube is mounted in a physical gimbal system representing our three rotation axes. The outer ring is yaw, the middle is pitch, and the inner is roll. Normally, these rings move in this yaw, pitch, roll hierarchy. But watch what happens when we pitch the cube up by 90 degrees. The axis for the outer yaw ring and the axis for the inner roll ring are now pointing in the exact same direction. These gimbals have become aligned. This is gimbal lock. When we yaw and when we roll, we perform the same motion. We have lost a degree of freedom.
Right. When you're either, if you're pitching downwards or upwards, even if you're rolling or you're doing yaw, both of them appear to be same, and you do not know what angle you have to control to achieve desired motion. So that is gimbal lock.
This can cause chaotic, uncontrollable spinning. So, while Euler angles are intuitive and easy to understand, their dependency on convention and issues with gimbal lock mean that they are not the best orientation representation in systems. In later videos, we will look at
So you might have seen quaternions coming into picture, right? Okay, so screen I want to change now. Okay. Okay, so I think you understood gimbal lock. So what do you want to do? You intend to control orientation with three independent rotations, right? Roll, pitch, and yaw. Roll, pitch, and yaw, but at certain configurations, you effectively get only two. So one rotation becomes redundant. That leads to loss of controllability. So it is not a physical lock, it is a mathematical singularity caused by how we describe motion, rotation, right? So, okay, I think this is clear. Okay, so what was the question that we were dealing with? Yeah. So the question says, which of the following representation orientation suffer from gimbal lock? It is Euler angles. Okay. So if we talk about rotation metrics, so rotation metrics represent orientation as a single global transformation, right? They do not decompose orientation into sequential rotations. So no axis collapse or align internally, right? So we do not have the problem. Second option was quaternions. So quaternions represent orientation as a unit vector in 3D. So along with this phi theta psi, you have another representation which comes into picture, and there is no intermediate rotation axis, so no singular configurations arise there. We'll have a question later on. And the third option was Euler parameters here, right? So for Euler parameters, it is same as quaternions, just a different name used in rigid body dynamics. So they inherit the same advantages. So correct answer is Euler angle, because Euler angles describe orientation as, okay, Euler angles describe orientation as three sequential rotations. All right. So when this is a problem, for example, pitch is plus minus 90 degrees in ZYX. So this becomes a problem. We lose 1 degree of freedom. Classic example is aircraft pitching at plus minus 90 degree. So yaw and roll become indistinguishable, right? Okay. I hope this is clear. Okay. So this is a question in which we have to, so this is highly mathematical, and I'll tell you how it has to be done. But transformation of a rigid body consisting of rotation about, so this is the vector about which we are rotating. We are not rotating about formal x, formal y, and formal z now. Rather, we are rotating about this fixed axis followed by a translation. Which of the following represents the homogeneous matrix, right? This is the question. First of all, do you know what is how do you define the complete homogeneous transformation? Does it only have rotation term or something else? Have you read about it? If I want to write a transformation matrix, what terms does it consist of? Some rotation term, that means some rotation matrix.
RD01.
Okay, yeah, that's true. So this is R, which is the rotation matrix. If it is for 3D, it would be 3 cross 3 rotation matrix. Then this is the translation term, which can be written as D. Then this is 0 vector over here, and this is 1. Right. So we want to uh, so we want to have a rigid body transformation about this 1 comma 1 comma 1. All right, and translation also. So how do we do this? Any idea how should we go about this? Okay, so I would request one thing from all of you. I'm not going to solve this question because that would not help you learn this concept. So I would suggest, can you guys take a photo of this question and come up with the answer in the next class? Or if we have some time at the end today, then also. Please take a photo of this and you're supposed to solve this. How we can, so basically in each option, this corresponds to rotation matrix, this corresponds to transformation, and this is just zeros and ones. So we just have to find both of these and nothing else. Okay. That's it. And then we'll see. Okay. In this question, Euler parameters, which I said about quaternion. What does it consist of? It consists of, what is the correct answer for this? Can anyone tell me? Gimbal lock problem is not there. That means they do not suffer from singularities. Apart from that, they consist of 4 parameters, which is given by axis of rotation and the rotation angle. Okay, so we have the axis of rotation and the rotation angle, which actually helps us to know what is the quaternion. I'll see if I can show you a video. Yeah, I got a video that I can show you.
Spotlight shine bright all on me. Got the internet turn like, who is she? Whole world watching me.
In a moment, I'll point you to a separate website hosting a short sequence of what we're calling explorable videos. It was done in collaboration with Ben Eder, who is. Viewers of this channel would certainly enjoy the content of his, so do check it out. This collaboration was something possible is complete experience for yourself. Certainly one of the coolest projects I've had the pleasure of working on. Number system that the 19th century versions of Wolverine and the Old Man from Home Alone called evil for how convoluted it seemed at the time. And perhaps you too are wondering why on earth anyone would bother with such an alien-seeming number system. A nice way for describing 3D orientation, which is not susceptible to the bugs and edge cases of other methods. I mean, they're interesting mathematically for a lot of reasons, but this application for computer graphics and robotics and virtual reality and anything involving 3D orientation is probably the biggest use case for quaternions. To take one example, a friend of mine who used to work at Apple, Andy Matuszczak, delighted in telling me about shipping code to hundreds of millions of devices that uses quaternions to track the phone's model for how it's oriented in space. That's right, your phone almost certainly has software running somewhere inside
your phone is pitching most of the times, right? Euler angles alone won't suffice
of it that relies on quaternions. The thing is, there are other ways to think about computing rotations, many of which are way simpler to think about than quaternions. For example, any of you familiar with linear algebra will know that 3x3 matrices can really nicely describe 3D transformations. And a common way that many programmers think about constructing a rotation matrix for a desired orientation is to imagine rotating an object around 3 easy-to-think-about axes, where the relevant angles for these rotations are commonly called Euler angles. And this mostly works, but one big problem is that it's vulnerable to something called gimbal lock, where when 2 of your axes of rotation get lined up, you lose a degree of freedom. And it can also cause difficulties and ambiguities when trying to interpolate between 2 separate orientations. If you're curious for more of the details, there are many great sources online for learning about Euler angles and gimbal lock, and I've left links in the description to a few of them. Not only do quaternions avoid issues like gimbal lock, they give a really seamless way to interpolate between 2 3-dimensional orientations, one which lacks the ambiguities of Euler angles, and which avoids the issues of numerical precision and normalization that arise in trying to interpolate between 2 rotation matrices. To warm up to the idea of how multiplication in some higher dimensional number system might be used to compute rotations, take a moment to remember how it is that complex numbers give a slick method for computing 2D rotations. Specifically, let's say you have some point in 2-dimensional space, like 4, 1, and you want to know the new coordinates you'd get if you rotate this point 30 degrees around the origin. Complex numbers give sort of a snazzy way to do this. You take the complex number that's 30 degrees off the horizontal with magnitude 1, cosine 30 degrees plus sine of 30 degrees times I, and then you just multiply this by your point, represented as a complex number. The only rule you need to know to carry out this computation is that I squared equals -1. And then, in what might feel like a bit of black magic to those first learning it, carrying out this product from that one simple rule gives the coordinates of a new point, the point rotated 30 degrees from the original. Using quaternions to describe 3D rotations is similar, though the look and feel is
you need to have the magnitude, you need to have the angles, and then you can project it, basically.
slightly different. Let's say you want to rotate some angle about some axis. You first define that axis with a unit vector, which we'll write as having I, j, and k components, normalized so that the sum of the squares of those components is 1. Similar to the case of complex numbers, you use the angle to construct a quaternion by taking cosine of that angle as the real part, plus sine of that angle times an imaginary part. Except this time, the imaginary part has 3 components, the coordinates of our axis of rotation. Well, actually, you take half of the angle, which might feel totally arbitrary, but hopefully that's going to make some sense by the end of this whole experience. Now let's say you have some 3D point, which we'll write with I, j, k components, and you want to know the coordinates that you'd get when you rotate this point by your specified angle around your specified axis. What you do is not just a single quaternion product, but a sort of quaternion sandwich, where you multiply by q from the left and the inverse of q from the right. If you know the rules for how I, j, and k multiply amongst themselves, you can carry out these two products by expanding everything out, or more realistically by having a computer do it for you. And, in what might feel like a bit of black magic, this big computation will return for you the rotated version of the point. Our goal is to break this down and visualize what's happening with each of these two products. I'll review the method for thinking about quaternion multiplication described last video, and explain why half the angle is used, and why you would multiply from the right by the inverse. On the
Okay,
screen
so
now,
you can follow this for more details and all. It is by 3 blue, 1 brown. By the way, this is one of the most important channels that you should look at when you want to learn very good physics, when you want to know something out of the box that you haven't thought of. This 3 blue, 1 brown is the best channel to watch, okay? I recommend watching this channel. Okay, so let's go to this. Now window. So I hope these are clear. These are not the minimal representation, right? Because in Euler angles, we just have 3 and that is the minimal representation. And they are not same as the Euler angles. Okay. So Euler parameters or quaternions use 4 parameters, avoid singularities, but are not minimal, and they're definitely not Euler angles. Okay. A rotary joint connects two rigid bodies in 3D space. Which of the following is true? This is directly from the lecture. Can someone tell me? So if they are not connected, let's say they are individual, how many degrees of freedom does this have? This also has 6 degrees of freedom. This also has 6 degrees of freedom, right? I hope that makes sense. This has 3 translational and 3 rotational. Similarly, this. Both of them have independently 6 and 6 degrees of freedom. But if they are connected, what would be true?
6 plus 1 degree of freedom.
Okay, and why do you say that?
6 plus 1 7 degree of freedom.
Why would you say that? Like, what is your logic behind it? Seven is the correct answer, but why? Why don't we have 12? How did we come to 7 number from 12?
Well, there is 5 constants. So
Okay.
12 minus 5 constants in this case.
That is correct. Perfect. Very good.
12.
So what happens? In this, we would have 12 in this case. But in this case, what happens? We are, so for example, if there is a rotary joint, a revolute joint in 3D, it only allows rotation about one axis, right? So since it is interconnected, this would have initially 6, this would have initially 6, but these are connected. So you are restricting the motion. Whatever x this has, this would also have the same x. Whatever y, I mean, not have the same x, but have that degree of freedom. If for y also it would have the same degree of freedom, for z also. But what are the constraints? You cannot have 3 relative translations, and you cannot have 2 relative rotations, right? You can have one. You can have one. Why? Because this is a rotary joint and it can rotate. So this you can have. Apart from that, there are only 6 possible. It can roll pitch here, it can go in x, y and z direction, but apart from this, this revolute joint, this rotary motion is only possible, and the 5 constraints are imposed. So 12 minus 5 is 7. So the rotary joint allows only one relative degree of freedom between the two connected rigid bodies, right? And the system of 2 rigid bodies have 1 degree of freedom. This is wrong. 6 is also wrong, and 7 is correct, as we saw. 6 would mean 2 bodies would behave as individual rigid bodies. So this is wrong. This would require a fixed joint and not a rotary joint, but it is a rotary joint. All right. So the fourth one is the system of 2 rigid bodies have 7 degrees of freedom. So 6 degrees of freedom for overall rigid body motion of the assembly, and 1 degree of freedom for joint rotation. So I'll write here 6 degrees of freedom for overall rigid body motion of the assembly, okay, and 1 degree of freedom for joint rotation. All right, I hope this makes sense. So a revolute joint adds 1 internal degree of freedom to a system that otherwise moves as a rigid body with 6 degrees of freedom. All right. Okay. So let's move to the next question. So this is here we are talking about spherical joints, and SS pair in a loop gives rise to what? How many constraint equations is the question. Okay. So let's see. So what does SS pair mean first? Spherical joint to spherical joint, and each spherical joint allows 3 rotational degrees of freedom. No translation is allowed at either joint. Okay. So what happens? So locally an S joint imposes 3 constraints on relative motion, right? So now we are talking about open chain and loop. When joints appear in an open chain, what happens? Each joint adds its own constraint, right? But if it is in a loop, what would happen? Many constraints become dependent. Only independent loop closure count. Loop closure constraints count. Okay.
Do you have a class here?
No, I'm teaching.
That's what it's from.
Okay. So independent loop closure constraints count. Okay. So what would happen if there is SS pair in a loop? Fixing the distance between, so an SS pair connects two bodies by fixing the distance between two spherical joint centers, allowing free rotation about those centers, right? So the only geometric requirement is there is one scalar equation, a distance constraint. Only this distance constraint is my uh, equation. So even the positions are 3D and rotations are 3D, the loop closure imposed by an SS pair only enforces constant length between the two joints, right? That just gives one equation. So we just have one constraint equation. All right, because all of them independently could have done, but since it is a loop closure, that means everything becomes fixed. Both the rotational constraints become fixed, and once that becomes fixed, only thing is that we have one, like, everything becomes fixed and we have one constraint equation for this distance. So only the distance between two spherical joints is constrained, and the distance is one scalar constraint. And so if in one of the options they are saying three constraint equation, that would imply fixing the relative position vector, which an SS pair does not do. And in case of 5 also, that is wrong only, because that would correspond to something like a revolute joint. And no constraint option is also wrong, because the distance must remain constant between the spherical joints. So that is all we have. All right. So an SS pair in a loop constrains only the distance between 2 points, giving one scalar loop closure equation. All right. So there are many other scenarios in which you can have SS, we already saw, but RR and SR pairs, etc. So for SS pair, you saw that there is only one scalar equation and only the distance between two joint centers is fixed. But and here we just had rotation about 3 axes and no translation, and then we found out that there is just one constraint equation. But if it is an revolute joint, what would happen? It constrains 3 translations and 2 rotations, right? We already saw that we just have 7 degrees of freedom, and we have 3 translations and 2 rotational constraints. So if it is in a loop, then what would happen? It would lead to fixed distance and fixed axis alignment, and then from there we get 3 independent scalar equations, but I won't go into that. But this is how you look at it. Okay, now after this, what I have to share is very important. Okay, this is DH parameter. Okay, so DH parameters, why do we actually need DH parameters? Can anyone tell me the full form of DH? Come on, full form.
Deniver-Hartenberg
Right,
parameter.
right. And why do we need it? So we already have 6 degrees of freedom, right? If we get an access to all of X, Y, Z and all the roll, pitch, yaw angles, why do we need, yeah, why do we need even DH parameter? Like, if you have gone through the lectures, you might have seen we need just 4 parameters instead of 6. So what we do, we actually fix how our Z is going to point. Z is fixed. For revolute joint, it has to point, the z-axis has to point along the axis of rotation, and for prismatic joint, it has to point along the axis of translation. This is already fixed. Now for x, you just have to fix that it has to be along the axis, x-axis between the joints, right? That is how we do, and there are many more rules which I'll take forward. But before that, uh, okay. So everyone is aware that there are Modeling and analyzing. What do you want to model? So I'll write these steps in detail, but I'm not writing now because I want to show you. So I have a suggestion for you that I think I need to switch my screen. Okay, so this we already saw, and here this is what I taught in one of the courses in advanced robotics, and it covers a lot on DH parameters. Okay, because and there were many questions starting from the basics to a bit forward. All of them were there, so I'm sharing the link with you. You can go and watch it. It is on my YouTube channel itself, and apart from this, in advanced robotics playlist you'll have many other things that would be useful to you. So if you need, you can watch all the initial lectures. Okay, so this is a link that I'm sharing you, and I'll play it as well right now. So this actually gives you what DH parameter is, and we will have one 2R manipulator question over here with 2 revolute joints, that how do we write the DH parameter for the same. And then for 3R we actually have the question right now also, so we'll do that, but let's see for 2R manipulator with very basics. Okay, DH parameter, as said, okay, I have gone through the lecture. So this is the recorded video from the last year, and it was done for advanced robotics course. So you might see on the first slide I have advanced robotics for a slide, so it was done for there. Okay, now you can see here. And okay, so I hope you all have gone through the lecture, and DH parameter, as said in the slide, it is a very systematic way to describe the geometry of robotic manipulators. So if it were not there, what you would do is you will go on defining thetas and everything, and you'll have to do a lot of geometric calculations. It is reduced somewhat using the DH parameter, and there is a formula which you have to go on using again and again. You need not calculate everything and go on solving the things. Stop me wherever you find any problem, okay? Again and again in different with respect to different axis of rotation, with respect to different translation. You don't need to do that. So it actually standardizes kinematic analysis. It also simplifies the forward and inverse kinematics. So forward and inverse kinematics is something that you'll be seeing in the next week. We will also be seeing in the next week. So you might be going through the lectures for them. So I hope you understand the difference between forward and inverse kinematics. If not, we'll have a problem for the same. It also reduces the number of transformation matrices needed. So you might require more number of transformation matrices for going from one frame to another, but yeah, in this case it is reduced, and it is very systematic way of doing things. So the advantage of this DH parameter, yeah, the advantage of this DH parameter is that it simplifies transformations, means you have less manual calculation to go from one coordinate frame to the other. It is a standardized approach, so it has consistent frame assignment. You might have seen that Z axis is always placed coming out of the plane, and it is always kept parallel. So there is a rule that if you have a revolute joint, all the Z axis should be in the direction along the axis of the revolute joint. If it is prismatic joint, then you must have the Z axis in the axis of that prismatic joint movement. So this is standardized approach, whereas you won't have these if you are going to follow if you're not going to follow DH
Ma'am, your
convention.
voice is not coming.
Voice is not coming. Is this not audible? Hello? Okay. Then it is a compact representation. Is it audible now? Because for every
Yes,
link we
yes,
just
audible.
have four parameters. Okay. And should I start from a bit back, I guess? You need not calculate everything and go on axis of rotation with respect to different translation. You don't need to do that. So it actually standardizes kinematic analysis. It also simplifies the forward and inverse kinematics. So forward and inverse kinematics is something that you'll be seeing in the next week. So you might be going through the lectures for them. So I hope you understand the difference between forward and inverse kinematics. If not, we'll have a problem for the same. It also reduces the number of transformation matrices needed. So you might require more number of transformation matrices for going from one frame to another. But yeah, in this case, it is reduced and it is very systematic way of doing things. So
Ma'am, again voice
the
issue. I
advantage
cannot
of this
hear
DH
anything.
parameter. Oh, is it not audible? Okay. Yeah. The advantage of this DH parameter is that it simplifies transformations. Means you have less manual calculation to go from one coordinate frame to the other. It is a standardized. Is it audible now?
Ma'am, your live voice is audible, but the recorded session is not.
Okay, so that is creating a problem. Okay, then how do I share these with you? Approach. So just a second. So I have shared the link with you, right? In the chat box. I do not have these slides right now with me, so it's difficult for me to. Okay, so what I'll do is I'll use it has Excel. Just a second. So see what we are doing. From here only I'll tell you. So what happens with DH parameters is that it simplifies your transformation. It reduces your manual calculation between the coordinate frames, right? Because we just have 4 parameters now and we do not have all the parameters that we need to deal with while we are multiplying with rotation matrices and looking at thinking about translations and everything. Apart from that, it is a standardized approach because you always have to have the z-axis along the axis of the revolute joint or along the axis translation and axis of the prismatic joint. Then it is a compact representation and it has efficient calculation because you see that you'll make a table and then you are going to substitute the value and you'll get the answer. So yeah, in software also, in MATLAB also, we'll see it is very easier. It just has to go in one it just has to go in one this matrix and then you are going to get all the answers. So we'll see how we do that on MATLAB. And it reduces error with predefined or repeated formulas. It's just that you have to know the method and you're going to get the answer. Okay, so moving on to the first slide. So other slide. So what you see, we are basically concerned about 4 parameters over here. Okay. So what do we actually do? Let's say if this is a revolute joint and this is a revolute joint, this is a revolute joint and this is just the end effector. Okay. So what we'll do? So for this revolute joint, this is called the base, right? So for the base is something which is not rotating and it is fixed. Okay. Now you can place your first link also there. Okay. So what we do here, we first define everything in world frame. So here my Z is pointing out of the plane and X is along the link. X naught can be defined arbitrarily anywhere because of for the base link we do not have any link. Okay, but X1 which would start right away after this for each link, what is going to happen? For x1, we will have it pointing in the direction of the in between the revolute joints, and z1 will also coincide with z0. Basic thing is in link 2, x2 would be along the link between the two revolute joints, and so here they do not, I think, say it to be base, it is also a revolute joint. Okay, this is also a revolute joint. So what do we do here? We have in the world frame, we have z0, which is fixed basically. Z0 is fixed and x0 is pointing in some arbitrary direction. Now for this first joint, which is this joint, we have x1 in the direction of the link between the two revolute joints and z1 in the direction of z0. Okay, now for the second joint, what do? We take z2 again to be the axis of the revolute joint, which is pointing out of the plane, and x2 along the direction which joins both the revolute joints. Z3 also same thing. So this is how these things are like, this is the basic convention that we follow. Okay, so z is the axis of rotation on the translation, and x-axis is the shortest distance between the two z axes. Okay, we'll see that in more details what we are doing. Okay, then after this, the important thing, so these are basically the parameters a, alpha, a, theta and d, where alpha is the link twist, means it is basically the angle between the z axis. Okay, then a is the link length. Okay, theta is link offset, I think they say. I think I'll tell you, no, not link, d is the offset, and theta is the angle between the two z x axis. So we'll see that. Just let me come to the right part. Okay, so we'll see this example, 2-DOF planar manipulator. Okay, so let's see this example. So this is 2R manipulator with two revolute joints. One revolute joint is here and the other revolute joint is here. Right? Now what do? We define the link lengths and the two angles. Okay, so let's say the length of the first link is L1 and the length of the second link is L2, and both of them are theta, the angles which they make with the horizontal axis. Here it is theta 1 and here it is theta 2 with respect to the first link. Everything that we want to care is with respect to the link preceding it. Okay, now from here we want to find the position and orientation of the end effector, which would be essentially placed over here. Okay, so it is basically, so what happens? Okay, so here we try to find out. Now you see how the axes are defined. That is the most important thing. Okay, so this is a revolute joint and this is a revolute joint, but we have to have a fixed base, right? Now how you'll take the fixed base? Fixed base has to have z-axis coming out, z-axis as the axis of the revolute joint. So z-axis, z0 points out of the plane. Okay, how x0 should be defined? It can be arbitrary because it is just placed in the world frame. We care about z1 even more. Now what happens? Now this z0 can be placed somewhere here also, but it is about the distance only. It just gets more calculative. So to avoid that, we have this link in the same frame as the z0 is z1 is going to sit. So for z1, what do? We have axis coming out of the axis aligned to the revolute joints axis, and then x1 is along the direction of the link, means it has to be the shortest distance between the revolute joint axis. So this is x1, right? After this is x2. Again, it is pointing in the direction of the link, and it is along the length of the link, and z2 is aligned along the axis of the rotation. Okay, so if we, so these are the values that are given to us, and after that, if we want to, for 0 to 1, like for this joint, if we want to write a, alpha, d and theta, what it would be. So so what is a for between x0 z0 and z1? Is there any distance? There is no distance, right? Because both of them are coinciding. Is there any angle in between z0 and z1? No angle. Is there any distance between the x of this? Is there any distance between the x-axis, x0 and x1? No, they are intersecting, so the distance is also 0. And about the angle, that is where we have to care. You see that the angle between x0 and x1 is theta 1. So we write theta over here. Alright. After this, for link 1 and 2, what do? We see the distance between link 1 and link 2 along the x-axis. We get it to be L1. Okay. We look for the angles in between both of these x-axis, Z1 and Z2. Okay. What do we find? Z1 and Z2 both are coming out of the plane. So there is no angle between them. So it is 0. Now, the distance between the x, so you see x1 is like this and x2 is like this, they both are intersecting, so the distance is 0, and the angle between x1 and x2 is theta 2. So this is your DH parameter table. Okay, a, alpha, d, theta. We'll write in detail also what it is, but you see how it is being done. Now after this, what we'll do? Once we have all of this written, then we will write this. Why we are writing this? Because all the rotations are taking place about the z-axis. So the rotation, the axis of rotation for us will always be z-axis, right? Now, we write cos theta 1, sin theta 1, 0, and sin theta 1, cos theta 1. You have already seen this is rotation about the z-axis. And once we get this, it is happening about theta 1, right? So this is the transformation for going from link 0 to link 1. Okay, if you are at link 0, how do you go to link 1? What is the transformation matrix? It is translated by 0, 0, 0, right? Because it is at the same base, but it is rotated. And this is the rotation matrix that you have directly plugged in from here. Okay, now what if we want to go from 1 to 2? You see there is an L1 term also coming here, which is related to translation, and there also we have seen that in manipulator it is a link offset by L1, right? So if we, so here we can substitute the value of theta 1, theta 2, etc., right? Once we have this, we get the proper transformation matrix for going from link 0 to link 1. Okay, now for joint 2, for going from link 1 to link 2, what we'll do? We have again a rotation matrix which has this multiplied by theta 2, right? And once it has this angle theta 2 over here, and then it has the same rotation matrix is there, and then we have L1, 0, 0. L1, why? Because in the x direction we are moving, because we have aligned our x with the link, right? So L1 is the offset that we have for the link. And then we can substitute the values here for going from 1 to 2. Okay, once we write this, the total transformation matrix for going from 0th link to the second link would be what? To the second configuration would be what? It would be basically a multiplication of both the transformation matrices. So what do we do here? We write the transformation matrix, the first one, and multiply it with the second one, and we get this. We get this matrix after multiplication. All right. So we are finally interested in the end effector position, the x, y, and theta of the end effector. And if you see it, it would, from here you can just find out that the position would be 0.707, 0.077. Anyway, we are not doing anything in the z-axis, so this would remain 0, and you will have this as the translation, and the rotation matrix would correspond to this first 3 cross 3 elements. Okay. So, if you are supposed to find out what is the orientation, we already know that the first term is cos theta, second term is minus sin theta. You can find tan theta, and from there you get at what angle this is oriented. Okay, this is what we do. Now, let's say you have 3 revolute joints. What you are going to do is discussed here. Okay, you can always do it. This is important. Yeah, this is something that we obtain by simplifying everything. Let's say we have some theta, we have some alpha, we have some a, and we have some d. Then what is a transformation matrix that we get between two links, I minus 1 to I? This is the matrix. So what you do in MATLAB, you just take this matrix, you plug it over there, you substitute the values, you get a transformation matrix directly. Okay. Transformation. Okay. So if you want to watch in more detail, you can watch this. So from here you can see yeah. So this is one of the rules as sorry, x-axis, right? Very good. So as per the DH notation, if the two axes z-axis are intersecting, then x-axis is taken where? So x-axis in that. So initially what we wanted the x-axis to be in the lie in as a particular distance in between the two z-axis, right? If it is a revolute joint or even if it is a prismatic joint. But in this case, if they are intersecting, then we take the x-axis orthogonal to the plane containing the z-axis if they are intersecting. Okay. Then the parameter that indicates the link length in DH table is what? A is the link length, alpha is the link twist, which is taken which is the angle basically in between the z-axis, and then d is the link offset for what is the distance between them, and theta is the joint angle. Okay. Okay, I hope this is clear. This is for 3D manipulator. I think I'll do it here. But apart from that, you can see that here we have MATLAB problems at the end. Okay, in this video lecture, and it covers DH parameter in detail. You can watch this lecture and then use it, like understand how to implement this in MATLAB. We'll have many MATLAB problems coming up, but this is where you can learn it now itself. Okay. Okay. Now I'll switch the screen. Which WhatsApp group? I'm not aware of any WhatsApp group. I pasted the link here. You can use it. I do not know about any WhatsApp group. I'm not in it. Pasting the link again. Okay. So, okay. So if we talk about this question, what do you think is the correct answer to this question based on whatever we have seen? We just want to know about the convention, which of them is correct.
Second one is correct. Coordinate system I1 is attached to the link I minus 1.
Are you sure about it? Is it I minus 1 or I? Whatever we do with the same. Actually, the correct answers are this and origin of lie. So when I showed you this thing in this way, right? Here it was 0 because we have to consider the base configuration. Now if I don't consider the base here, maybe I'll take another ground here and then I'll consider the base configuration here, but it would just be an offset over here. So instead of just not exploding our calculation without any use, what we do, we place z0 axis over here, but z1 is also here, and this is the first joint and this is the first link. So shouldn't it be coordinate system of I is attached to the link I and origin of I lies on the joint axis I? When we are talking about this link, we are talking about this joint, the first one itself. This revolute joint cannot be 0, right? 0 is just for fixed frame. But if you have a joint or a prismatic or a revolute joint, any joint, you have to have the first frame there. Okay. So the answer is A and C. We have to do everything with the same I. Okay. So each frame I is associated with link I and joint offset I. So it is not with I minus 1 because in one of the okay, I should not talk about it here, but it is modified DH parameter, but we won't go into there. Okay, so zi axis is aligned with the joint axis I and origin of frame I lies on that axis. All right. Okay, after this in DH convention used in this course, link. Deepak, do you want to say something? Please mute yourself. Okay, thanks. Okay, so in DH convention used in this course, link offset DI is measured along joint ZI from XI to XI, is always positive, is always constant if I is rotary, is always constant if I is prismatic. What is it? What is exactly DI? It is measured along joint ZI from XI minus 1 to XI, or okay. So Zi is a joint axis I, Di measures the offset along that axis, right? So the reference points are x minus 1 and xi, or you can say xi and xi plus 1. So if we are going to have some link offset, it has to be measured along which axis? It has to be measured along x-axis. Okay. Is it always positive? No, it is not always positive. And Third option is always constant if joint I is rotary. If it is rotary, yes, this distance will, the distance between the two joints would remain constant, and is always constant if prismatic. No, for a prismatic joint, the di changes with motion. So the correct options are this. I think I should be writing a lot of things. Wait, that would clarify the things even more. Okay, so what do we do? The basic steps are assign, sorry, attach frame I to link I. Okay, we first do this. Once we are done with this, then the last frame is attached to the end effector. Okay, once we are done with this, we want, the most important thing is how do we define the z-axis. Okay, this is the most important thing. And what do we do? Zi is always aligned with the axis of joint I. This is non-negotiable. Okay, it works for both revolute joint and prismatic joints. For revolute joint, it is rotation axis. For prismatic joint, it is translation axis. Now, we want to define the x-axis. Okay, xi is along the common normal between zi minus 1 and zi. So the common normal is basically the shortest line perpendicular to both the z-axis, and there are two edge cases here. If zi minus 1 intersects zi, then xi is any line perpendicular to both. Okay, if if zi is parallel to zi, then xi is in the perpendicular direction. Okay, these are the two cases. Then we define the origin. The origin of frame I lies on the z-axis and at the intersection of z and x-axis. Definitely, we don't need to be writing that. Y is chosen according to the right hand coordinate system. So basically x cross y should be z. Just this. The most important thing, AI is distance along x in between two z-axis. Okay, alpha I is angle about x between the two revolute joint axis or whatever axis, basically z-axis. Di is distance along zi minus 1 and theta I is angle about zi minus 1. Okay, so okay, so then we have the transformation order and everything. So this is what we do now. Let's say we have this robot with us. Okay, and then we want to find out what is the DH parameter. How we'll go ahead? This is the base. This is not a revolute joint. This is just a base. This is R, this is R, this is R. Okay, 3R manipulator. What we'll do? You're just supposed to find out alpha a di theta I ai minus 1. Okay, now you just have to be careful. So the first two options, can you see L1 and L5? Do you think L1 and L5 would come to the picture when I am writing the DH convention? Yes or no? Yes, and why do you think so? So, actually, the issue is what should come in DH parameter. Okay, it should be something which is happening in between the joints and not because the extended part or the base part is there. Okay, let's say you have yeah, so this is after writing this convention, this is just an extra length. Okay, when we talk about this joint, we don't have a joint here for which we want to take any offset, or here also we do not want. We're just attaching the frame here, so it won't come. Okay, so we are only concerned about these joints. All right, so that won't come. Now, then what should come? Can anyone tell me what all things will come into picture? Like, can I have a list of the things that would define this? We already have them in option, although. Can you guys tell me which would be the correct answer? Okay, tell me, do we have alpha I or not? This is incorrect and this is incorrect for sure. And here you get to see L1. So this is also incorrect. So from here by elimination only you can say this is correct. But why? Do you see any angle between the z axis, z0 and z1? If I have, let's say this is just an extra, if I have z0 over here and I also have z1 over here, which is basically the, sorry, so my bad, z0 over here and z1 also over here, which means the revolute joint axis along this, both of them, for both of them I'll have 0, right? Alpha means the distance between them, it would be 0, right? Di means the distance between their both x-axis. So let's say if x0 lies here and x1 in this direction, so the distance between them is 0 because there is no intersection between them. But is there any angle in between both of these x-axis? Do we have an angle? Yes, that is theta 1. Okay, similarly, when you talk about the second joint, what do you get? You'll get any angle between the two revolute joints? No, both are pointing out of the plane, right? Both of them are parallel, so it's 0. And do you have any distance between these joints, these x z axis? Yes, it is L2, right? Do you have any so here it would be x2, right? Do you have any distance in between these x's? No, you don't have, right? So it is 0. Do you have any angle in between these x? Yes, it is theta 2, right? Now, let's talk about this joint. It has the axis pointing in this direction, which is perpendicular to the axis here in this case, right? The axis is perpendicular to that of 2. So pi by 2 would be the angle between the z axis. right? The distance between z axis is given by L3, right? Because this is the difference. Now, if you want to have x axis, it would be along this direction, right? X3. And here the x was x2. Do you have any offset between them? Do you have? You see here we have a quantity called L4. So the x-axis here and the x-axis here have an offset of L4. So L4 you get here, and the angle, is there any angle difference between both of these x-axis? Yes, it is rotated by theta 3. So this is your DH parameter for this 3R joint. All right. Any confusion with this DH parameter? I can clarify it. Please let me know. No confusion? Okay. Then let's move to the next question. This is the last question. I won't be solving it, but I want the answer from you. So what is happening here is it appears to be too small, right? So it is RPS joint, revolute, prismatic and spherical joint. Okay, this is R, this is wait, this is R, this is P, and this is S. Okay. For this system, we want to find out what is the DH parameter. So basically, you have to find between link 1 and 2. Okay. And then you have to come up with an answer. This we'll discuss in the next class, because I want you to watch the lecture that I've shared with you and then identify it, and then we'll see what is the answer. You just have to see if you're getting the same answer. Okay. So, Lakshmi, why did you write no? I think Acha, it was for some question. Okay. Okay. So, what I'm saying is, I have shared a lecture with you, right? Do watch this lecture. Apart from this, we have the whole this thing playlist. So, just a second. So if you so you get to see this MATLAB problem also here, right? Apart from that, if you see the channel properly, there are four playlists over here. Okay. One of them is for control system, the other is also for control system, so it is twice. And apart from that, this is the lecture which I'm taking now. I'll be uploading every video here, but apart from that, this is the advanced robotics wala playlist. All right. No, yeah, yeah. So this
Hello,
is
everyone.
what happened. This is your wall, and then you have a so this has all the lectures uploaded. So the first lecture was a very basic one, but from the second, you have a lot of things to learn from here as well. You might not want to go into the last few lectures, because that is somewhat related to some advanced concepts and everything, like pipettes and all, and grasping. But the basic lectures that we have in the beginning are all that you should see. All right. So if I can share the link to this playlist, I'll share it. Yes. You should watch this. And the week 2 lecture which I showed you today was this DH parameter wala video lecture. So you should go through it. It also has MATLAB problems covered, which I did not get time to cover today. So please go through it and please understand DH parameters in detail. It has been covered very well here. Okay. And is there any other confusion that you want to ask or something? Else we are done with the session.
No, ma'am. Thank you.
Okay. So I guess there are no more questions. Then we'll close the session.
Madam,
Huh.
please, how to use MATLAB?
MATLAB will have some questions. Do you have MATLAB already installed with you?
No.
Okay, so you can use MATLAB online. So you make an account on MATLAB online.
Okay.
And once you make the account there, you'll be able to run all the programs. So as I told you, for DH parameters, you should see that lecture, and there are a couple of questions there which you should try to practice. Yeah, the basic syntax and everything is there in the video which I have shared with you. So you just have to like open a new script, write the program there and run it. That is it. And if you're using any programming language or are aware of any programming language, then you can use it. Like if you are aware of any programming language, you will basically know the syntax. The syntax is a bit different over here in MATLAB, but then the concept and the logic remains same, right?
Okay.
So it won't be difficult. It's just that you have to use MATLAB online and you can start practicing the questions there. We'll have some problems in some of the sessions. DH parameter I did not have because it is already covered over there, and you can look there and you will be able to solve parallelly. C and Python, everything is fine as long as you're able to apply the logic, it is fine. MATLAB you should also learn. So that's why I'm saying. Because for matrix operations and everything, MATLAB is more clear than Python. But Python is also clear only, it's not a problem. If you're aware of any of the languages, it's just a change in syntax and then you'll be able to. Okay, any more questions?
Okay, ma'am. Thank you.
Yeah.
Thank
Okay.
you.
Okay, then we'll meet in the next class on Monday at the same time. Thank you. See, bye.